Alrighty, good morning, lads and ladies. Welcome back to Calc 1. Today, as promised, we're going to have the full story of areas between curves. That's about it, really. We'll also talk a little bit about exam 3, which is right around the corner. So let's get into it. Not sure which of these is still alive. So we are almost done. The term is very nearly over. Here we go. Which means, of course, our last midterm is coming up. Your guys' last day of class is the 23rd, which is next Friday. So here's what I'm thinking. We'll do exam 3 Monday, right? Monday the 19th. We said this last week, but I just want to make sure we're all clear. Okay, and a little announcement. I guess there's another announcement also here. Unfortunately, I've been called for jury duty. I think I mentioned this last week. I have my first actual jury thing tomorrow. So I'm hoping that it doesn't take too long. But there is a small possibility that I will not be here on Wednesday. I know it is hypothetically possible that this thing goes on for quite a while, but it is certainly my hope that it does not. If it ends up being a long-term thing, then what I will do is I will record the lectures in the evenings when I get home and post them. In place of the Zoom meetings, you'll just have links to YouTube videos. That will be the plan. I know it's not quite the same, but I'll do my best to rearrange things in a way that works. It's also starting to get, threatening to get in the way of office hour routines. Again, if that happens, I will just shift them to the evenings. And again, I know it's not ideal, but my hope is that this doesn't last that long. If need be, then we'll just move the time slots around as necessary for the office hours, and the lectures will be posted as videos. The good news is today's actually the last day of new content for the class, right? We are a little bit ahead of schedule. So today you're gonna get the full story of areas between curves, the last little bit of new stuff you need to learn for this class. And then from here on out, we're just kind of getting ready for the exam, getting ready for the final, and that'll be the end of the course. There are one or two other little extra topics that I like to talk about. I kind of save them for the end of class, depending on how much time we have. Things like the mean value theorem for integrals and Newton's method, but yeah, that's about the story. So last time, we saw, to find the area between two curves given as functions of x, y equals f of x, and y equals g of x from x equals a to x equals b, or you could say on the interval a to b. You just have to integrate the upper function minus the lower function. This is f, this is g, here and here respectively. If the thing that I want is the area between these suckers, there are a couple ways we could think of it. We could think of it as the area under F minus the area under G. Or we could think of it as coming from these little Riemann rectangles whose heights are defined as, F minus G at any given point. So that area is equal to the integral from a to b of the upper function minus the lower function. And we saw an example with sine and cosine where they swap places, right? You had to switch which one was upper and which one was lower by finding the points of intersection, and then doing separate integrals, right? Doing one integral where cosine was above sine, and then a separate integral where sine was above cosine. But this is the basic picture. So I'd like to begin today with maybe one more example where things are not given quite as clearly, and then talk about a more general case here, because the assumption that's baked into this is that these two things are functions of x. That's almost always the case in the problems that we've looked at in this class. Pretty much every time we're doing an area problem or anything to do with integration, anything in general, we've had this situation where our curves are functions of x. But that need not always be the case, and there are some special cases, for instance, where x is a function of y, or where maybe neither of those things are true, that we can still find the area between two curves. So we're going to look at all of that today, but first a kind of gentle example. So let me pop up the textbook, we'll grab one here. Oh, sorry, one more word before examples. People have been asking me, how do I study for the final? How do I study for exam 3? How do I study for the final? So first and foremost, you need to do the homework, right? You need to solve the homework problems until you are 100% comfortable with them. Then, of course, the study guide. Now, I'm going to be releasing your study guide today for exam 3 because that test is 1 week from today. So keep up with the homework, solve the study guide problems as soon as you can. The next thing that I would recommend is to look at the chapter reviews in the book. All right, you'll notice they've got some tricky concept questions. They've got some sneaky true-false questions. These are exactly the sort of things that people get into trouble with on my tests, right? People always ask me, how do I study for the true-false problems? How do I study for these really concept-focused multiple-choice questions? Well, by solving true-false problems and concept-focused multiple-choice questions, which the book is packed full of. Now, for exam 3, you wouldn't want to look at the chapter 2 review or the chapter 3 review. Now, you would want to look at a little bit of chapter 4, right? Because 4.9 is back there. And you would want to look at chapter 5. Those would be the main things, especially chapter 5. So these sort of questions, I have put these exact questions, some of them on my test, not because I look in the book when I want to come up with those questions, but because some of these, like this guy, are just so important. It's really important that you understand these concepts, and it's really important you understand what you can and cannot do. And the idea is that by having practiced a bunch of problems, you should have a good feel for whether these are true or not. But you can look at these problems to get a feel for the types of things that might show up. The concept check questions are very good. The true-false questions are very good. And then, of course, the straight-up exercises would be a great way to get extra practice if you feel you are in need of that. So how to study for the tests. Solve the homework, work the study guide problems, make sure you've mastered those. The homework is the bare minimum. We talked about this at the beginning of the semester. Bare minimum. Solve the homework, work the study guide problems. After you've done that, look over old tests. That's more for the final. Look over old tests. and then go into the chapter reviews of the book, right? Solving problems is the #1 most important way to study. So solve homework problems, solve study guide problems, make sure you can solve all the problems from the chapter tests. That again is really just for the final, or sorry, the midterm test, that's just for the final. And then get into the book and solve some review problems, right? The textbook is your friend. Okay, so we were here not to do anything from chapter 5, but to look at some areas between curves problems. Here's the setup that we saw in class on Friday. And of course, the result is that you integrate the upper function minus the lower function. So let's look. Yeah. So here's the actual definition of the area between the curves. They say integrate the absolute value of f minus g. Of course, this all comes down to figuring out whether f or g is bigger. So you don't need to stress too much about that. What we have in covers that. And you see here some of these things. There is no clear upper and there is no clear lower. That's what we're going to be getting to today. But before I do that, I want to just grab one little problem, like number 9 down here. Number 9 looks good. So we want to find the area bounded by the curves y equals 1 over x, y equals 1 over x squared, and x equals 2. And first, we're going to sketch the region. All right, so sketching these curves, hugely important. Let's see. So each of these is something you should know, right? In fact, these are curves I expect my college algebra students to know. This is a hyperbola. This is kind of like a hyperbola. It's an even function whose shape in quadrant 1 is very similar to 1 over x, but goes to 0 faster. And this is a vertical line going through the point 2, 0. You could always plot some points if you're unsure what they look like. Here's 1 over x. We know that the point 1, 1 is on there. So I'll label this as 1, 1. 1 over x squared goes through 1, 1. The point on 1 over x at x equals 2 is 2, 1/2. The point on 1 over x squared when x is equal to 2 would be 2, 1/4. It would be lower down here. So the curve 1 over x squared, he looks like this. And of course, the vertical line x equals 2 is a vertical line going through 2, 0. So this is x equals 2. This guy right here is 1 over x. And this guy right here is 1 over x squared. I think the only thing in this section that really challenges people, at least when it comes to these more basic problems, is not knowing the graphs. So take the time to learn the graphs. They didn't give me an A and a B here. They didn't say find the area between these two curves from x equals A to x equals B. They said find the area bounded by these curves. So what we need to do is look at this sketch and ask, where do I have a region, like a definite enclosed region? And that's right here. right? Every other little chunk of the plane that these curves kind of split it up into is open on one side. Right, like this is open over here, this is open up here. So the only place I actually have a bounded enclosed region is right here. We want to identify our upper function, our lower function, A and B. That's all we need. So my upper function here, if we watch this, this is 1 over x, remember? So from x equals 1 to x equals 2, in fact, from 1 to infinity, 1 over x is bigger than 1 over x squared. So my upper function here is 1 over x, and my lower function is 1 over x squared. All right, so the area is equal to the integral of what's my upper function? It's 1 over x minus my lower function, 1 over x squared dx. And this integral is going to be done from x equals 1 right here, because that's where my region starts, to x equals 2 right here, because that's where that region ends. This boundary curve, x equals 2, chops things off there. And this intersection point, x equals 1, is what starts the region. So this is the integral from 1 to 2 of 1 over x minus 1 over x squared. Any questions about how we set this up, where I'm getting this integral of these pieces? Okay. So now I need an antiderivative, right? The way we evaluate this and any other definite integral is by finding an antiderivative. I can take antiderivatives of each of these pieces separately because there's a minus in between them. The integral plays nice with addition and subtraction. So this would be the natural log of the absolute value of x. That's my antiderivative for 1 over x. Minus, this minus is this minus. An antiderivative for 1 over x squared. Well, let's see, 1 over x squared is x to the negative 2. So this would be x to the negative 2 plus 1, which is x to the negative 1, divided by negative 1. And then all of that is evaluated from 1 to 2. If you want off to the side, we can say, antiderivative for 1 over x dx. This is ln absolute x plus c. Antiderivative for x to the negative 1. Sorry, x to the negative 2 dx is x to the negative 1 divided by plus c. That's sort of the things from your antiderivative table I'm using there. We don't write a plus c here because it's a definite integral, but these are the entries from that table that I'm calling back to. I can simplify this piece just a tiny bit before I start plugging things in, and I should. So this is the natural log of the absolute value of x. This minus down here, this negative 1 factor downstairs, is going to make this whole piece here negative, which is going to change this minus to a plus. And then x to the negative 1, that's just 1 over x. This is what I'm evaluating from 1 to 2. And we plug in the upper bound and subtract what we get when we plug in the lower bound. This will give me the natural log of the absolute value of 2 plus 1/2, so parentheses, minus parentheses, the natural log of the absolute value of 1 plus 1 over 1. One over 1 is definitely just 1. What is the natural log of 1? What is this?
0?
Yeah, excellent. This piece is 0. The absolute value of 2 is just 2. So this is the natural log of 2 plus 1/2. And then minus 0 plus 1 is just minus 1. And these two combine easily, right? Plus 1/2 minus 1. There's no reason to not put those together into minus 1/2. So that would be my final answer here. Any questions on this photo? I'm simplifying this piece. So where did the 1 over x on this line come from? Remember, x to the negative 1. So if we want here, I can do a simplification on a separate thing. X to the negative 1 divided by negative 1 is 1 over x divided by negative 1, which is negative 1 over x. So this 1 over x is just coming from simplifying this piece. Since this piece overall ended up negative, this minus and the negative here come together to make that a plus. So yeah, these two are the same, just simplifying the upper one into the lower one. All right, standard problem, classic problem. Could easily show up on something like a test. It's about that level. Let's look at something a little bit more challenging, something we don't have an obvious framework for. Something like one of these. In fact, I'll make it a little bit simpler. X equals y squared. Um, I can try this. Let's just do it. So I want to find the area bounded by the curves x equals y squared and y equals 1/2 x minus 1. The challenge here is that most people aren't going to recognize this right away. Right? Depending on your pre-calculus class, you may or may not have gotten a good enough treatment of conics to recognize this. This is a parabola, but it opens sideways. This is the curve x equals y squared. Y equals 1/2 x minus 1 is a line looking something like this. Right? Slope 1/2, y-intercept -1. Y equals 1/2 x minus 1. And the other curve here is x equals y squared. Again, you could get here by plotting points, or if you weren't sure, you didn't want to do that, you could take this and try to solve it for y. This would tell you that plus and minus the square root of x is equal to y. And this guy up here, this is the positive square root of x. This guy down here is the negative square root of x. But we do need to be comfortable graphing things like this. You will see things like this in your homework this week. The other weirdness here is that there is no consistent upper and lower function. And we could handle this a few different ways. But by far the most natural one is, instead of working with x as your variable, turn your head sideways and work with y as your variable. You see, when I turn my head sideways or my paper sideways like this, now I do have an upper function and a lower function. And they never trade places, at least not in the region I'm looking at. So I want you to hang in here with me for a second, because this is important. This is my x-axis, and this is my y-axis. The increasing x direction is like this. X gets bigger and bigger the further we go to the right. So instead of upper minus lower, which is what we have when we crane our neck like this, we can look at it like this, but we just need to think of that integral setup as being a right minus left. The other thing we need to do is make sure both equations are solved for one variable. You see, this one is solved for x, but this one is solved for y. So here, what I'm going to do is the key. Instead of integrating upper minus lower, we work with y as the variable and integrate right minus left. So I'm thinking of y as being my independent variable. That means I'm going to rewrite this in terms of the variable y. So y equals 1/2 x minus 1 is equivalent to saying y plus 1 equals 1/2 x, which is equivalent to saying, now multiply everything here by 2, we get 2y plus 2 is equal to x. Now, if I want to find this area, I will integrate the right function minus the left function. So this right function here is the same as x equals 2y minus 2. And this guy was already solved for x, is x equals y squared. My right function here is this guy. My left function here is this guy. So to find this area, we must integrate my rightmost function, which is 2y plus 2, minus my leftmost function, which is y squared. And the integral is done dy. This is what we mean when we say we're working with y as the variable. Another way to say this is you could set up a little Riemann strip in here. You can imagine a little Riemann rectangle in here. It looks like this. His thickness is a little vertical thickness, so that's a dy. And his height or length, if you want to call it that, is this right function, call it xr, minus this left function, call it xl. So xr is 2y plus 2, and xl is y squared. So you integrate right minus left instead of upper minus lower. The catch is we need to find these y values. I need to know my bounds, my limits of integration. So I'll call this y value up here b. I'll call this one down here a. It does matter here, yeah. So it's a question in chat. Does it matter which one we choose to solve for? Could we solve for x instead of y? So I did solve for x, right? Both of these are solved for x. And that was the idea, is that I wanted both of these solved for x so that I could think of them as curves where x is a function of y, rather than where y is a function of x. So I chose to solve both of these for x, because that lets me set up this integral, right? This is my one function solved for x, 2y plus 2, right? If I solve that linear function for x, I get this down here, which is 2y plus 2. The other one was already solved for x. Here, x equals y squared, x equals y squared. The reason we want to think of it like this is because there is no nice and clear upper and lower, right? If we try to look over here, my upper and lower are defined by the same curve there. These are both coming from x equals y squared. And then over here, if I try to think of upper and lower, now my upper is the x equals y squared curve and my lower is the linear function. So at the very least, I would have to split it up here, and then it would be a little bit tricky to figure out this region, and this region would be somewhat natural, but not entirely obvious. So if I want to do all of this in one integral, it is necessary to think of this as a function of y, and to think of this as a function of y, which means we have to have both of those curves equations solved for x. Now there is a matter to deal with here still. I don't know these bounds, right? We don't know these limits of integration. And I think they're going to be quite nasty. You may have noticed here me trying to deliberate between 1/2 x minus 1 and 1/2 x minus 1/2. I think because of the way I chose these bounds are going to be quite nasty. But can anybody suggest how would we find them? How would I find this y value b here and this y value a here? The y values where these curves intersect. Yeah, very good. We set the equations equal to each other. So I'm going to take y squared and set it equal to 2y plus 2. So let's do it. Find the limits, the bounds we need to solve xr equals xl, right? Where's the left curve equal to the right curve? I can try to move back through and fill in details. So right now, what we're doing is finding the points where these two curves intersect, specifically finding the y values where these two curves intersect. All right, so we said we're going to integrate from A to B, the right curve minus the left curve, where A is the y value down here, and B is the y value up here. In order to find A and B, I need to set the equations for these two curves equal to each other. So I'm going to take x equals y squared and set that equal to x equals 2y plus 2. In other words, I'm going to set y squared equal to 2y plus 2. The solutions to this are quite nasty. Let's see, this is y squared minus 2y plus 2 equals 0. There's a whole bunch of ways you could solve this quadratic. I think completing the square is probably the fastest one. But I suspect that most of you would use the quadratic formula, so I'll do it like that. So this would be true if and only if, because this does not factor, y is equal to negative b, which is 2 plus and minus the square root of b squared, which is 4 minus 4 times 1 times 2. All over 2 times a, which is just 2. So this is 2 plus and minus the square root of, oh, sorry, b here is negative. So yeah, so b squared minus 4. Oh, does this not have this? No, minus 2i. Yeah, this is a minus 2. I'm sorry. So this is a minus 2. So this becomes 4 plus 8, which is 12 over 2. So when we subtract this over, we get y squared minus 2y. We subtract over the 2. This will also be negative. So this is negative b plus and minus the square root of b squared minus 4 times a, which is 1 times c, which is negative 2. So under the radical here, we have 4 plus 8, which is 12. And then the square root of 12 you can think of as 4 times 3. So that's 2 times the square root of 3. So that's 2 plus 2 root 3 over 2, which is 2 plus and minus, which is 1 plus and minus the square root of 3. So those are our two bounds. Solving equations like this is something I know you guys can do, but normally I wouldn't ask you to do this in the context of a problem, certainly not on an exam problem. You'll be able to find your bounds just by like factoring. So A is the smaller guy, 1 minus the square root of 3, and B is the larger guy, 1 plus the square root of 3. And the area is the integral from A to B. So that's the integral from 1 minus root 3 to 1 plus root 3 of 2y plus 2 minus y squared dy. The antiderivative step here is not bad. 2y has as an antiderivative y squared plus 2. 2 has an antiderivative 2y. And minus y squared is going to become minus y cubed over 3. And we evaluate from 1 minus root 3 to 1 plus root 3. I'll just go ahead and plug in here. We'll see what we get, and we'll leave it alone because the arithmetic is quite nasty. So this would be 1 plus the square root of 3 all squared plus 2 times 1 plus the square root of 3 minus 1 plus the square root of 3 cubed over 3. That's what we get when we plug in the upper bound to this expression. There's a big open paren at the start and a big closed paren at the end. And then I subtract what I get when I plug in my lower bound, which is 1 minus the square root of 3 squared plus 2 times 1 minus the square root of 3 minus 1 minus the square root of 3 cubed over 3, close. And now, if you were to take the time to blow all of these pieces apart, you want to FOIL this out, distribute this, cube this out, same thing with each of the pieces over here, there would be a lot of cancellation. The answer, this is the answer. It's just not in the nicest imaginable form. Because this was a little bit clunky, I'd like to look at least one more example of this nature. But before I do that, I want to ask you guys about the setup. So I'll hold here for a second. Are there any questions on how we found these bounds, or what we were doing to find them, or how we found this antiderivative? Any questions on like this page? Yeah, I will go back to the graph in just a second. All right, so coming back. Here's our graph. Any questions about how we got this graph? What we were doing with these expressions? So again, the big idea is instead of upper minus lower, we integrate right minus left. And the trick is that we're thinking of y as the variable. So you have to solve both of your equations for x, sketch the graph, and then you integrate right minus left instead of upper minus lower. The challenge here was maybe in drawing the graph, if you're not comfortable with graphs like these, and then also finding the numbers a and b. Just to be clear here, xl, the left curve, is y squared. xr, the right curve, is 2y plus 2. So we integrate the right function minus the left function. That's where this came from. Okay, let's try one more. This one I'll take from the book. We can go ahead and do number 4 here. Actually, let's do number 11, because here in number 4, they give us the graph. Number 11, they don't give us the graph. That'll give us the practice. So we want to find the area bounded by the curves 1 minus x equals 1 minus y squared and x equals y squared minus 1. The first thing we need to do is draw these graphs. X equals 1 minus y squared and x equals y squared minus 1. Does anybody know what the graph of, let's start with 1 minus y squared looks like?
Is it just down 1, but it's still that same sideways graph?
So if it was just x equals y squared, we know that that's that sideways parabola. It's not going to be shifted down in this case. It's actually going to be a left-right thing. But you're thinking in the correct way. So if this was y equals 1 minus x squared, everybody knows what that looks like, right? 1 minus x squared is a parabola opening down, vertex at 0, 1. Just flip everything over. So x equals 1 minus y squared. When you plug in y equals 0, you get x equals 1. So you know that the point 1, 0 is on this graph. I'll put 1 way out here. If you were to plug in x equals 0, then you get 0 equals 1 minus y squared. That has two solutions, positive 1 and negative 1. So here is the parabola. X equals 1 minus y squared. And you see, with me turning the picture sideways like this and not labeling the axes, it looks just like y equals 1 minus x squared. It's just sideways, rotated 90 degrees counterclockwise. So that's the curve 1 minus y squared. X equals y squared minus 1. Here, if I plug in y equals 0, I get x equals negative 1. So I know that negative 1, 0 is on that graph. Again, if I plug in 0 for x, I get 0 equals y squared minus 1. That has the two solutions, y equals positive 1 and y equals negative 1 again. So this guy is the mirror image of this guy. He looks like this. This over here is x equals y squared minus 1. So the one way you can go about graphing this, find the x and y intercepts. It's not that bad. All right, and the rules are the same as they've always been. To find x intercepts, you plug in y equals 0. To find y and solve for x. To find to find y intercepts, you plug in x equals 0 and solve for y. So my right function, again, we need to identify the region. Right? The region I'm looking at is the only region that's enclosed by these two curves. It's this kind of weird football-shaped region in the middle here. So within this weird football-shaped region, my right function is this guy, and my left function is this guy. So this is XR, and this is XL. And this time my intersection points, the y values that start and stop my region are easy to see. I think of my little Riemann rectangles as being like this. The y value at the bottom here is -1. The y value at the top here is +1. So the area in this case is the integral from -1 to 1 of my right function minus my left function. My right function is 1 minus y squared minus my left function is y squared minus 1. And again, these integrals are done dy. The variable is y. So before we move on, I'd like to stop here and take questions on how we set up this integral or how we got these graphs, because that is certainly the hard part. Okay. I want to emphasize that these bounds are y values. Right? This is my lower bound. It's this y value, and this is my upper bound. It's this y value. If I think of this as being full of little Riemann rectangles, those Riemann rectangles are oriented sideways, which means that they kind of start down here and they end up here. But from this point on, the problem is easy. Again, we're just integrating a polynomial. So this is the integral from -1 to 1 of, I have here 1 minus y squared plus 1. Just distributing the negative. The ones cancel. And we have integral from -1 to 1 of -2y squared. Combine your like terms. You can pop out the -2. And you have integral -1 to 1 of y squared dy. Questions so far? Okay. From here, antiderivatives are easy. We have y cubed over 3 evaluated from -1 to 1. So this is going to be -2 times 1 cubed over 3 minus -1 cubed over 3, which is -2 times 1/3. Minus here is going to make plus. -1 cubed is +1. This is 1/3. So we're getting -2 times 2/3, which is -4/3. I am a little bit bothered by this because it looks like this is coming out negative. So I'm thinking maybe I made a little algebra mistake. Did I do something stupid here? No, I honestly don't see it. 1 minus y squared is definitely the right one. So we plug in -0. So our answer here would definitely be 4/3 because areas have to be positive, and I'm confident of the rest of this. I'm just not sure. Honestly, not sure where the error is here. It might be an orientation thing. So holler if you see it. Did I swap one of these with the other at some point? Right. I'll admit ignorance. I'm not sure why I'm getting a negative here. Let me throw these in decimals and take a quick look. All right. And that's what we drew for 1 minus y squared. Y squared minus 1. So this is our right function. This is our left function, 1 minus y squared minus y squared minus 1. Let's integrate this from -1 to 1. We can make a teachable moment out of this. So when you're confident you've done everything correct, but your answer comes out negative, you know something has gone wrong, right? Because areas here certainly should be positive. Usually what it means is that you've swapped these two guys around. Usually what it means is that you subtracted in the wrong order. So that's what I'm looking for here. We do always integrate the right function minus the left function, because this is my increasing direction of x. And my right function certainly is 1 minus y squared. That's this guy. He is the right function in this region. This is definitely the left function in this region. So from -1 to 1, this guy should be larger than this guy. Did I just do something stupid algebra-wise? But I'm not seeing it. Oh, I see it. Well, all right. Who sees it? Follow when you do. We have a teachable moment here. I made a mistake. Can you guys see the mistake?
You have 1 plus 1.
Yeah, the ones don't cancel, do they? Yeah. I wasn't thinking. This one and this one, they certainly don't cancel. This isn't -2y squared. This is 2 minus 2y squared. So like you, I am human. Mistakes do happen. And this is a good way to spot them. Right? So we know we made a mistake. We know we made a mistake because this area should not come out negative. We're finding the area between two curves. Areas are always positive. There is no issue of signs here. So the fact that this came out negative tells us there's a mistake. We triple check that this curve was drawn correctly, this curve was drawn correctly, and that we're integrating right minus left. Desmos verified that, yeah, we drew this correct, we drew this correct. This one is the right curve, this one is the left curve, so we're subtracting in the correct order, which means we know that this line is correct. So the mistake had to be somewhere after that. And the mistake is right here. Yeah, those don't cancel. This is integral -1 to 1 of 1 minus y squared minus y squared plus 1, which is integral -1 to 1 of 2 minus 2y squared dy. So I apologize for the error. But it is a good thing to make mistakes and learn from them, spot the mistake. So if I were to integrate this, my antiderivative would be 2y minus 2/3 y cubed. That's what we need to evaluate from -1 to 1. Antiderivative for 2 dy is 2y. Antiderivative for 2y squared dy is 2/3 y cubed. Another common error I see here is people integrating a constant like this to x because we get in that habit. That's why it's always wise to write your differential. One of the reasons it's always wise. So now we'll evaluate this between the bounds. And we'll get our correct answer. This is 2 times 1 minus 2/3 times 1 cubed minus 2 times -1 minus 2/3 times -1 cubed. So that's 2 minus 2/3 minus, this is -2. And then this minus -1 cubed is -1, right? -1 times -1 is +1 times -1 again is -1. So this will become plus 2/3. And again, we need to be careful with the negatives. So I'll have 2 minus 2/3 minus minus here makes plus 2. And then minus plus here makes minus 2/3. So we have 4 minus 4/3. Clearly, I have not had my coffee yet. I am sorry for the mistake. Questions on this fellow? All right, let's try one more, and then I will let you guys go. Let's see, we did 9 and 11. Those are both flagged as challenge problems. What else looks good in here? I know generally trig functions are a little bit intimidating. What would be fun? We could do this one, or see secant squared. That's going to take a little bit of time to graph. Cosines 2 minus cosines. Fuck it. Let's do something scary. How about 15? Here we want to find the region, find the area of the region enclosed by y equals secant squared of x and y equals 8 cos x. Let's take this the same way we have been. Find the area bounded by y equals secant squared of x and y equals 8 times the cosine of x. And they specify from -pi/3 to pi/3. Okay. Everybody should know what the graph of cos x looks like. And 8 cos x is just that cosine wave scaled up by a factor of 8. I think it's less likely that everybody knows the graph of secant squared. So let me jog your memory really quick. Regular old secant of x is kind of this shape. Vertical asymptotes. And then this shape. And then vertical asymptotes. Down here, same sort of thing. It's a trig function, so it's periodic. The period is 2 pi, just like with cosine. This is y equals secant x. So can we figure out from this what secant squared looks like? Well, all of these negative bits are going to be flipped up and made positive. So when you square something, it is always non-negative, the output from a square. So the graph of secant squared, you just take all the y values on this blue graph and you square them, which will, again, make all these negative values positive. It'll also have some effect on the shape of these things, but not much. Since the y values here are all slightly larger than or equal to 1, right? This guy down here would be -1. This guy here is again -1. This is -pi/2, positive pi/2, 3pi/2. Everywhere cosine is 0, secant is undefined, has its vertical asymptotes. So these pieces will come up, and the shapes will get stretched out a little bit because the y values are all larger than 1. So down here, I'll do my best drawing of the secant squared graph that I can do in a few seconds. All right. I'm going to call this down here 1. And secant squared should look something like this, from -pi/2 to pi/2. I think a lot of people remember this as being a parabola. It's not. It's not technically a parabola. A parabola has this particular geometric definition. This thing is flatter on the bottom than a parabola is. But it's close enough, and if that mnemonic helps you, then that's okay. The vertical asymptote here is at -pi/2. And the vertical asymptote here is at +pi/2. Those are kind of the two central asymptotes here. And since we're only working from -pi/3 to pi/3, those are like in here. I don't actually need to worry about anything else that's going on out here. So this is the graph y equals secant squared x. And then I'll put the graph of the cosine function in orange so we can see a little bit better. 8 cos x, is the regular cosine function, but with its amplitude, scaled up by a factor of 8. So he's going to start way up here. And then you know that the cosine of pi/2 is 0. You know that the tangent line there looks about like this, like y equals -x. The tangent line over here looks like this, y equals x. So here is 8 times the cosine of x. And he continues doing his thing, but we don't particularly care about what he does outside this region. So the black is secant squared, and the orange is 8 cos x. Again, I'm looking for a region that's enclosed by these curves. Since all the other secant squared stuff, like the next piece of secant squared is going to be like this. And similarly over here. The only place these guys can enclose a region even is in here. This is the only spot I really care about. Periodically, there would be a symmetric region over here and a symmetric region over there, but they told me focus from -pi/3 to pi/3. So we're definitely looking at this piece. So that's the area I want. They were kind enough to tell us that they only want us to look from negative pi over 3 to pi over 3. But really, we should make sure we know what these intersection points are. They do happen to be negative pi over 3 and pi over 3. But it's an important step in most of these problems. So I want to show you how to do it. The intersection points here would come from setting secant squared of x equal to 8 times the cosine of x secant squared is 1 over cos squared. So we'd set 1 over cos squared x equal to 8 times the cosine of x. We could multiply both sides by cos squared. And that would give me 1 equals 8 times cos cubed of x. We can divide both sides by 8, and we get 1/8 equals cos cubed of x. And then taking cube roots, the cube root of 8 is 2. We get 1/2 is equal to cos x. And sort of the two solutions that are closest to 0, where x is equal to, where cos x is equal to 1/2, are pi over 3 and negative pi over 3. So x equals plus and minus pi over 3. Those are those solutions. So this is negative pi over 3. This is positive pi over 3. Those are both coming from the unit circle. So even if they hadn't told us negative pi over 3 to pi over 3, we would be able to find them. The last thing to do is to set up the integral. Here I do have an upper and a lower. There's no reason to mess around with right and left. I took cube roots. So what happened to the cos cubed here? I took the cube root on both sides. The cube root of 1/8 is 1/2, and the cube root of cos cubed is cos. Bueno. So then our last move here is going to be to integrate the upper minus the lower between those bounds. So that's the integral from negative pi over 3 to pi over 3. My upper here is the orange curve, which is 8 cos x, minus my lower curve, which is the black guy, is secant squared x. So I integrate the orange minus the black from negative pi over 3 to pi over 3. This is one of those cases where you can spot the antiderivative immediately. An antiderivative for 8 cos x is 8 sine x. And an antiderivative for secant squared x is tangent x. You could split this up and pop out the 8 and kind of handle each piece separately, but hopefully at this point we're getting a little bit more comfortable with the linearity of the integral. And then this gets evaluated between these bounds, negative pi over 3 to positive pi over 3. And you can check, if you differentiate 8 sine x minus tangent x, you will get 8 cos x minus secant squared x, because the derivative of 8 sine x is 8 cos x, and the derivative of tangent x is secant squared x. So the calculus step here is easy. All the work was in the setup, drawing the picture. Our last bit here is to evaluate between bounds. This is 8 times the sine of pi over 3 minus the tangent of pi over 3. All of that minus 8 times the sine of negative pi over 3 minus the tangent of negative pi over 3. So our last bit of work here is some unit circle stuff. What is the sine of pi over 3?
Square root of 3 over 2.
Very good. So 8 times the sine of pi over 3 is 8 times root 3 over 2. What is the tangent of pi over 3?
Square root of 3.
Very good, just root 3. What is the sine of negative pi over 3?
Negative root 3 over 2.
Yeah, remember sine and tangent are both odd functions. So this is 8 times negative root 3 over 2. That'll be negative 8 root 3 over 2 minus the tangent of negative pi over 3 is going to be negative root 3. So you can clean all this up. 8 root 3 over 2, that's 4 root 3 minus 1 root 3. That's our first param. And then we have minus negative 8 root 3 over 2 is negative 4 root 3. Negative 4 root 3. And then this is going to be a plus root 3. So we have 4 root 3 minus root 3, that's 3 root 3, minus negative 4 root 3 plus 3 root 3. So this is 3 square roots of 3 minus negative 3 square roots of 3, which is 6 root 3. Alrighty, that is all we have time for today. And with that, lads and ladies, we are actually done with Calc 1. Congratulations. You have suffered, scraped, and survived through every lecture that one must survive through in order to finish this class. The last few things we need to do, of course, is get you through your last midterm, which is going to be next Monday, and then get you through your final exam. And your final exam, we are close enough now, it's time for me to start saying this every day. Your final exam is the 28th. From 8 to 10 a.m. It is not the normal time. It is a day we normally have class. That's lucky. So the 28th, 8 a.m. I'll post some Canvas announcements. I'll definitely post an announcement with the link, of course. The final is going to run the same way our midterms run. It'll just be a comprehensive test. So next Monday, a week from today, you're going to have exam 3. That'll be on the 19th. Wednesday and Friday of this week, I'm going to cover a few extra little topics on Wednesday, and then Friday we can review for the test. I'll go ahead and publish your study guide today. You want to get working on that immediately, rather than giving you a whole separate homework for, actually, let me think about this. I'll probably give you a separate homework for 6.1. That way you're not, I don't want to overwhelm. So probably a short homework for 6.1. And then the study guide, rather than folding them together, that doesn't seem to be as effective. But watch WebAssign. I'll have more stuff out for you today. Please make sure you are working hard to get caught up on any homeworks you have not completed in the past. And remember what I said earlier today about the best way to prepare for the test. The best way to prepare for exam 3, make sure you've done all the homework, make sure you do the study guide, and then look in the textbook. Look in the textbook specifically. The chapter 5 review is going to be a really useful tool for y'all. Make sure you know all of the problems in the concept check and in the true false. Yeah, Fabrice, don't tell anybody you got this, but in case you don't have it, know that you all have technically paid for a copy of this thing, but not everybody has it. Not everybody wants to work with the copy that is in WebAssign because it's terrible. So if you want the PDF that I use in class, there it is. All right. That's it from me, lads and ladies. I will see you next time. Probably Tuesday. Will not have an office hour because I got to go back to court. But I will have my normal office hour this afternoon, and I'll be trying to schedule a couple extra ones in the evening to make up for those that I've been losing due to this jury duty bullshit. All right. Take care, guys. See you next time.